scholars. I hope that you and your family and loved ones are doing well. We at SEO are thinking about you every day. We care about you, and we're sending our best wishes. So usually in an SEO math class, we all rely heavily on your knowledge, your thoughts, and the ideas that you bring into the classroom. And there are many opportunities for you to talk with your classmates about an idea, or to come to the board, to share what you're thinking, to ask questions, and just in general to solve problems together. And so although much of these activities aren't possible when you're watching a video, I still encourage you to try to watch this video as if you were in a classroom actively. And so what this means is to take out your workbook or a notebook while we go through the lesson together and take notes in it, just as if you were in a classroom. Feel free to pause, rewind, and watch parts of the video a second time if you're confused. And make a note of things that you're still confused about after this lesson so that you can ask your instructor. All right, sounds good. So let's get to it. Today we're going to talk about average rate of change and learn how to calculate it and interpret it graphically. The punchline of today's lesson is that average rate of change and slope are essentially the same idea. The only difference is that in order to calculate the slope, we need to be talking about a line, right? A linear function. So lines have slopes, for example, but quadratics, parabolas, right? We can't say they have a slope. An average rate of change allows us to interpret overall, on average, within a particular interval of a nonlinear function, what is changing, how is it changing? And so it's basically calculating slopes of nonlinear functions. This idea is very important. It's going to lead us over the next few lessons into the most beautiful idea, mathematical idea ever created by humans, which is the idea of the derivative. And we're going to be able to use average rate of change and all of our knowledge of slope to get a sort of basic and clear understanding of the derivative concept. It's going to be a lot of fun. Okay, so let's start. So let's take a look at this think, pair, share, and I'm going to scroll down so we can see the picture. So you decide to get away from the city and go for a walk in the woods. During the walk, you see a man-eating grizzly bear 500 feet away from you. The bear sees you and starts running. So there's the bear, and there is Gnarly, wondering if the bear is his mom. So our question is, what information about the running bear would you want to know? And there are many ways to answer this question. I would say that for me, the two pieces of information that I would want to know, the first would be the direction that the bear is running, directionality. Is he running towards me or away from me? I would say that's important. And the second thing I would want to know is the speed at which the bear is running. Now that speed, of course, might not be a constant speed. That speed might be changing. So that's the third thing I want to know. Is the speed changing? Is the bear slowing down or speeding up as he runs towards or away from me? So these are three things that I'd want to know. All right, let's keep going. Example number 1. So the function table below shows the distance between you and the bear as a function of time. So the distance is a function of time, and we're given some information about some of the questions that we had. So after certain amounts of time have passed, this is the distance between you and the bear in feet. So we're going to be able to answer some of those questions about directionality and speed and changing speed. So we can measure the average rate of change. This is the purpose of this lesson, which in this case we're talking about average speed, right? Because our units are distance and time, and we know that speed or velocity is just distance over time, right? In this case it's feet per second. These are our units, feet per second. So we can calculate this using this formula, which is change in distance over change in time, which should look very similar to the slope formula, right? Delta y over delta x. How is y changing as x changes by 1? How is the distance changing as time changes by 1 every second, right, for example? So let's use this formula to calculate the average rate of change over some intervals. Okay, so in the first 5 seconds between time equals 0 and time equals 5, what is the average speed of the bear? So I'm going to just keep our table in front of us so we can see where we get this information. So here we're going to want to calculate 450. Right? This is the relevant numbers. So we're going to do 450, the change in distance, right? Because that's where he ended up after 5 seconds. So that's the end minus where he started. 500 over 5 minus 0. So this right here is our average rate of change calculation. And we get negative 50 over 5. And we get negative 10. And again, we're talking about feet per second. So the average speed of the bear is negative 10 feet per second. So wait a minute. Speed, right? We're talking about the difference between speed and velocity. So speed shouldn't be about negatives and positives. It should just be how fast they're going, right? So this is actually more accurately velocity. The negative right here is telling you that the distance between you and the bear, right? That's what we're talking about, is getting smaller, right? So the distance is shrinking. So the distance is shrinking, which means the bear is running towards you. Okay, so that's how we can interpret that negative. And he's running towards you on average at a speed of 10 feet per second. Now, does that mean that every second he's running at you 10 feet every second? So if we say second number 1, 10 feet, second number 2, 10 feet, second number 3, is that what this is saying? No, this is not saying that. This is just saying if you saw the bear and you closed your eyes and you opened your eyes 5 seconds later, that bear had moved 50 feet. It could have been that the bear for the first 4 seconds didn't move at all, and then the 5th second he sprinted. You don't know. That's why we're talking about average. We're saying over this entire interval, we know that the average rate of change, the average speed, was 10 feet per second. Okay, let's keep going. Part B, so between time equals 5 and time equals 10, what's the average speed of the bear? So we're going to use the same sort of reasoning and formula to sort of solve B, C, and D. And so I'm going to just speed up the video, do it a little quickly to save us all time. Okay, so we've calculated the average rate of change between 5 and 10 seconds, 10 and 15, 15 and 20, and we notice that the speed at which the bear is running towards us, again, that's what that negative sign is doing, is moving from, on average, 15 feet per second to 20 feet per second to 25 feet per second. So we can interpret this as the bear is speeding up, which is not good news for us, and is an example of when a rate is changing, in this case when a speed is changing. So this is when we say the bear is speeding up. In physics we call this acceleration. This is exactly the difference, or the definition of acceleration. It's change in velocity over change in time. Just the same way velocity is change in distance over change in time, right? So acceleration sort of takes it up another level. So this is an example of the bear accelerating towards us. All right, let's keep going. Example number 2, graph the 5 points on the function table. So this is the table that we just used to calculate average rates of change. And then the question is asking that we found that the average rate of change was negative 10 over this interval, negative 25 over this interval. And where do these values show up in our graph? Okay, so let's do this step by step. So first off, let us graph these points right here. So one of the points was 0, 500. I'm going to do it in red so we can see it. 0, 500. There is a nice point right there. All right, so here are our 5 points. And now let's go back to the second part of the question, which is where do the values that we found, the average rate of change values, where do they show up? on the graph? Where can I see negative 10, for example, given this graph? And the answer is average rate of change is slope, right? They're very, very similar concepts. So over the interval 0, 5, that's between this point right here and this point right here. It's saying that if you drew a straight line between those 2 points, the slope of this line would be negative 10. And again, the negative, right? That is in fact a line with a negative slope. What about this interval over 15 and 20? So let's just move the graph up a little bit. So this interval we're talking about is right here, right? We already did the interval from 0 to 5. Now we're talking about 15 to 20. Well, here's the point at 15. Here's the point at 20. If I drew a perfectly straight line between those 2 points, it means that the slope would be equal to negative 25. So that is how we graphically interpret average rate of change. Now I just want to be clear that this is not saying that the graph or that the movement of this bear is made up of 5 or in this case 4 straight lines, right? The actual graph is probably a little smoother, right? So you may have maybe a little bit like that, right? Like that. It's not linear at all, so it's more, in this case it's actually quadratic. So none of these lines, they don't overlap with the actual graph, but they are on average within particular intervals how the distance is changing, right? So that's sort of the big idea here. Okay, let's keep going. So if a function is decreasing, what can you say about the average rate of change? And same question for increasing. Well, we just saw that if a function is decreasing, that's what we were just dealing with, the average rate of change, or slope, is going to be negative, right? Because the function is decreasing. And conversely, if a function is increasing, the average rate of change is going to be positive. Great. All right, let's keep going. So let's do a quick summary of how we can describe graphs and their rates of change. So here we have 4 graphs, right? 1, 2, 3, and 4. So in this graph right here, the function, is it increasing or decreasing? Well, clearly it's increasing from left to right. So we can write increasing here. Here we're decreasing, right? From left to right. Here we're decreasing, and here we're increasing. And what we just learned was that increasing functions have positive rates of change. Decreasing functions have negative rates of change. So that's pretty straightforward. So if we want to ask, how is the rate of change itself changing? This is the idea of sort of upping it from velocity to acceleration. Is the rate of change itself increasing or decreasing? So one way to make sense of this, and then I'll show you a trick, is to consider 2 average rates of change as the graph, as we trace the graph from left to right. So let's just do this real quick. In this example, an average rate of change on this part of the graph could look something like that, and on this part of the graph it could look something like that. And so you want to ask yourself, this slope, the slope of this line, which is average rate of change, it's positive, and the slope of this line is positive, but which one is more positive, right? So this slope is more positive, and this slope is less positive. And so if I'm going from a larger number, so maybe this number is 7 and maybe this number is 4, right? Is that average rate of change, is it increasing or decreasing? And so the answer here is it's decreasing, right? It is decreasing. So let's do the same thing over here. Here I have a slope that's negative, something like that. And here I'm going to have a slope that's more negative. Let's plop some numbers in there. This is a nice strategy in general, is to plop some numbers down and see if we can use those numbers to make sense of the problem. So this slope, maybe it could be like -2, and it's steeper, right? So it's like -5. So if I go move from -2 to -5, I am decreasing, right? So this is also an average rate of change that's decreasing. Let's take a look at this one. This graph is sometimes it's a little tricky because look, there it is going down and we're decreasing and negative. But again, let's take a look at our examples. So I could have an average rate of change here that's maybe like a negative, I don't know, 8, right? It's pretty steep. Average rate of change here is maybe closer to a -2, right? So when I move from -8 to -2, I'm increasing values, right? By getting less negative, that is an increase. So even though this graph is going down, we know that it is a decreasing graph. We know that its average rate of change is negative. Its average rate of change as the graph, as we move from left to right, is in fact increasing because it's getting less negative. And this one right here, we can see the graphs are getting steeper in the positive direction, and so this is also going to be an increase. Okay, here is the shortcut for that. Notice that both of these graphs have a decreasing average rate of change. If you put those graphs together, you have a sad face, right? So that's a decreasing. Both these graphs have an increasing average rate of change. You put those graphs together and we're very happy. So there's your shortcut when you're thinking about how to interpret average rates of change. And let's just do one calculation. So we can use our formula. Again, this formula is essentially the slope formula, only instead of y2, y1, x2, and x1, we're using function values because we're not dealing with lines, right? With linear equations, but everything is staying the same here, right? So this y2 right here, this is the function value f of b, okay, right? So here's right. This could be our our y2, y1, right? x2, x1. It's the same idea. We're still calculating slope. We're just doing it in a nonlinear function. So this is how we can calculate it, and let's just do a quick calculation. So here we're being asked to calculate the average rate of change of the function f of x is x squared between x equals 3 and x equals 5. So we'll sort of do it a little explicitly here. So we know that the average rate of change from our formula is going to be f of b minus f of a all over b minus a, and in this case our function is x squared, and in this case we could say that our a value is 3, right, and our b value is 5. That's fine. Those are the 2 points. So f of b is going to be 5 squared, right, minus 3 squared, because again our function is x squared, all over 5 minus 3. And we can calculate that. That's 25 minus 9 over 2, otherwise known as 16 over 2, otherwise known as 8. And what this means is that if you drew a graph of y equals x squared, something like this, okay, y equals x squared, and I said between x equals 3 and x equals 5, there's the point x equals 3, there's the point x equals 5. If I drew that line, the slope of that line would be 8. And that's the big idea. Great, I hope you enjoyed this video and stay safe.